Good morning. My name is Zamira. My roll number is 21951A04A1. I am pursuing my first year ECE in Institute of Aeronautical Engineering, Section B. Today my topic is note on normal form of spatial stiffness of matrix. Outline. Introduction, pursued properties, type of support. Introduction. The systematic development of slope deflection method in is this matrix is called as stiffness matrix. This method is a powerful tool for analyzing indeterminate structures. Stiffness method of analyzing of structure, also called as displacement method. In the method of displacement are used as the basic unknowns. Procedure. Determine degree of kinematic indeterminate of structure. Select unknown displacement. Restrain all the joints to set for fully restrained structure under given condition. For analysis of restrained structure to get ADL, generate stiffness matrix of given structure. Apply unit positive displacement for members and add all the displacement for members meeting at a joint. Superposition equation. AD is equals to ADL plus S into D. AD is equals to joint action or force given in structure. ADL, force analyze of restrained under given loading. S is equals to stiffness method. D is equals to unknown. Determine the final moment. Calculation for SF and draw SF DM diagram. Properties of stiffness matrix. Stiffness matrix is a square matrix of order n into n, where n is equal to OKI. Stiffness matrix is symmetrical matrix, hence Sij is equals to Sij. SII is equals to represent actions due to unit positive displacement, and while other displacements are zero. SII is the principal diagonal element. Stiffness matrix does not exist for unstable structure. Stiffness matrix is non-singular matrix. S is not equal to 0 for unstable structure. Si is the action at joint due to unit value of displacement at J joint. Global stiffness matrix. Assembly of global stiffness matrix of entire frame after computation of global stiffness matrix K of I of the members. The next step is the assembly of global stiffness matrix of the entire structure. In the previous cases examined, the A4 mentioned matrix resulted from the assembly of the global stiffness matrix of the structural members, and more specifically from their submatrix corresponding to their end nodes. Nevertheless, in the examined frame, due to the presence of combined node, the assembly of the submatrix of the global stiffness matrix of the structural members becomes rather difficult, and this assembly will be implemented term by term. Thus, based on the global stiffness matrix of the individual element, equation 7.6.2, the global stiffness matrix of the frame is given as the table is given below. Static condensation method. Assembly of global stiffness matrix of the entire frame according to modeling consideration. After computation of the global stiffness matrix K of I of each member, the next step in the analysis is the assembly of global stiffness matrix of the entire structure. This assembly, similarly to the analysis step E of consideration I, will be implemented on stiffness term by term basis. As a result, taking into account the element of the global stiffness matrix of the frame member which correspond to the global DOF equations 9.5.14 and 9.5.33b. The global stiffness matrix of the entire frame is obtained as the table. Fundamentals for finite element method. Imposition of displacement constraints. The global stiffness matrix K in equation 3.96 does not usually have full rank. because displacement constraints supports are not yet imposed, and it is non-negative definite or positive semi-definite. Physically, an unconstrained solid or structure is capable of performing rigid movements. Therefore, if the solid or structures is free of support, equation 3.96 gives the behavior that includes the rigid body dynamics. If it is subjective to dynamic force, if the external force applied are static, the displacements cannot be uniquely determined from equation 3.96. For any given force vector, it is physically meaningless to try to determine the static displacement of an unconstrained solid or structure that can move freely. For constrained solids and structures, the constraints can be imposed by simply removing the rows and columns corresponding the constrained nodal displacements. We shall demonstrate this method in example problems in later chapters. After such treatments of constraints, and if the constraints are sufficient, the stiffness matrix K in equation 3.96 will be of full rank and will be positive defined PD. Since we have already proven that K is symmetric, K is of symmetric positive definite property. Internal Hing's and modified stiffness matrix method. Assembly of global stiffness matrix of entire frame. After computation of global stiffness matrix Ki of frame member, the next step in the analyze is the assembly of global stiffness matrix of the entire structure. In the previous examined example, the forementioned matrix resulted from the synthesis of global stiffness matrix of structure members, and more specifically of submatrix of member end nodes of this matrix. In the examined frame, however, due to the presence of internal release roller at node 2, the assembly of submatrix of the global stiffness matrix of the members becomes more cumbersome and is more convenient to implement the term by term procedure of section 7.6. Thus, with the help of equations 8.5.2, equation 7.6.2b, and equation 7.6.2c, the global stiffness matrix of entire frame is given as red numbers correspond to global DOF of figure 7.15 colored in green. The table shows the given statements: assembly of elements matrix and vectors and derivation of system equation. Assemblage of element equation. Once the element characteristics, namely the element matrix and element vectors, are found in a common global coordinate system, the next step is to construct the overall or system equation. The procedure for constructing the system equation from the element characteristic is the same regardless of type of problems and the number and the type of elements used. The procedure of assembling the element matrix and vectors is based on the requirement of compatibility at the element nodes. This means that at the node where elements are connected, the values S of known as nodal degrees of freedom or variables is the nodal variables are usually generalized displacements, which can be translations, rotations, curvatures, or other spatial derivations of translation. When the generalized displacements are matched at a common node, the nodal stiffness and nodal loads of each of elements sharing the node are added to obtain the net stiffness and the net load at that node. Let E and M denote the total number of elements and nodal degree of freedom, including the boundary and restrained degree of freedom, respectively. Let theta denote the vector of M nodal degree of freedom, and K the assembled system characteristic matrix of order M into M. Since the element characteristic matrix K at the element characteristic vector P of E are the order n into n and n into 1 respectively, with n indicating the number of elements degree of freedom, they can be expanded to the order m into m and m into 1 respectively by including zeros in the remaining locations. Thus, the global characteristics matrix and the global characteristic vectors can be obtained by algebraic addition. Has 6.9 k is equals to e1 of e, and where K of E is the expanded characteristic matrix of element E of order m into m, and P of E is the expanded characteristic vector of element E of order m into m. Even if the assemblage contains many different types of elements, equation 6.9 and 6.10 will be valid, although the number of element degree of freedom n changes from element to element. In actual computation, the expansion of the element matrix K of E and vector P of E to the sizes of overall K and P of is not necessary, can be generated by identifying the locations of the elements of K of E and P of E in K and P respectively, and by adding them to the existing values of E changes from 1 to E6.2. This procedure is illustrated with reference to the assemblage of four one-dimensional elements for the planar truss structure shown in figure 6.3 of A. Since the elements lie in the xy plane, each element has 4 degree of freedom as shown in the figure 6.3 of B. It assumed that a proper coordination transformation section 6.1 was used and K of E of order 4 into 4 and P of E or 4 into 1 of elements E is equals to 1 to 4 were obtained in the global coordination system. Planar trust as an assembly of one-dimensional elements for assembling, and P of E. We consider the elements one after another. For E is equals to 1, the element stiffness matrix and the elements load vector P of 1 can be written as shown in table 6.1. The location row and column M of any component Kij1 in the global stiffness matrix is identified by the global degree of freedom theta 1 and theta m corresponding to the local degree of freedom theta I of 1 and theta j of 1 respectively. For I is equals to 1 to 4 and j is equals to 1 to 4, the correspondence between theta 1 and theta I of 1 and that between theta m and theta j of 1 is also shown in table 6.1. Thus, the location of components Kij1 in K will be shown in table 6.2. Similarly, the location of components of the elements load vector P of 1 in P will also be shown in table 6.2. For E is equals to 2, the element stiffness matrix K of 2 and the element load vector P of 2 can be written as shown in 6.3. As in stiffness matrix K and P of I of 2 for I is equals to 1 to 4 in global load vector, P can be identified. Hence, these elements would be placed in K and P at appropriate location as shown in table 6.4. It can be seen that if more than one element contributes to stiffness K of K, then the stiffness Kij of E for all the elements E contributing the K are added together to obtain KIM. A similar procedure is followed to obtain P of 1 of P. Application of spatial matrix introduction. The main role of spatial weights in their use as the basis of for construction of various tests for spatial auto correlation. These measures consist of compromise between attributes variables similarly and local and location and locational similarity, with the latter formally expressed through the spatial weights. However, the weights are also important for the creation of spatial explicit variables. These are variables that take into account the values observed at neighbor locations. There are two important applications for this. One pertains to construct of so-called spatial lagged variables for inclusion in a spatial regression specification. The other yields on approach to smooth rates by drawing strength from the values in neighboring observation. This takes the form of spatial smooth rates. We consider each in turn. For the spatial edged variables, we will continue to use the data set with point locations of house sales for Cleveland O OH. For the spatial smoothing examples, we will use the Ohio County cancer cases. Objectives: create a spatial lagged variable has an average or sum of neighbors. Create a spatial lagged variable as a window, sum or average. Create a spatial lagged variable based on inverse distance weight. Create a spatial lagged variable based on kernel weights. Wrestling coordination to obtain inverse distance weights. Compute and map spatial smooth rates. Compute and map spatial empirical base smooth rates. Getting started. To start, we continue to use the data set that contains the location and sales price of 205 homes in a core area of Cleveland, OH, for the fourth quarter of 2015. We also need to have several spatial weights active in the weights manager. At the very least, we need k nearest neighbor weights for k is equals to 6. Inverse distant weights using the k nearest neighbors with k is equals to 6 and Covey kernel weights, again using the adaptive kernel for k is equals to nearest neighbor and with the kernel applied to the diagonal weights. The diagonals will thus equal 0.75. We can either create these weights in the current projects after dropping the file cleave underscore SLS underscore 154 underscore core dot shp into the drop files. Here, rectangle of connect to data source dialog or load a project file that contains the weights. In the example shown in figure 1, the three weight files are cleave underscore SLS underscore core underscore K6 for KNN contiguity, cleave underscore SLS underscore 154 underscore core underscore K6 ID for inverse distance applied to the K is equals to 6 nearest neighbors, and cleave underscore SLS underscore 154 underscore core underscore K6 page for the Pankinoff kernel weights. Figure 1 highlights the properties of the latter as listed in the weights manager. Note how the kernel to diagonal is set to true. Thank you for giving me this wonderful opportunity. I am ending my topic here.